Good afternoon. So, the first speaker of this afternoon is Gautam Mandal from TFR Mumbai, and he'll be speaking on some results on thermalization in integrable models.
Can you hear me? So let me start by thanking Manus and other organizers for giving me the opportunity to speak here. So I'm like an outsider to this community, so thanks for the opportunity. And so I'll be talking about some results on thermalization in integrable models. So it's some work which started around 2013, but some of the techniques go way back to the early 90s. And these are my collaborators involved in the three parts of the talk that I hope to talk about. So let me start with a little introduction. So I'll be talking about thermalization. So classical picture of thermalization comes from ergodicity. If the system is ergodic, at long times the phase space point moves around in the codimension 1 submanifold given by some constant energy E. It spends equal amounts of time in equal volumes of phase space. Hence the long average of phase space quantities equals average over ME, which is a submanifold. A quantum mechanical version of this statement would be that if you start from a pure state, perhaps way of preparing it could be quantum quench. And then you take a time average like that, and then that as the time, big time t goes to infinity, then it should go to the microcanonical ensemble defined as such. So that's the statement about the time average. Sometimes one wishes to make a statement about the long time behavior without the time average. So now from everyday experience, it appears that starting with a system in a pure state, say a piece of metal, under some quantum quench, which is like a hammering, it gets thermalized, it becomes hot. So similarly, it appears, so this is a black hole context, which comes from a string theory context. It appears that under a gravitational collapse, a pure state built out of an ingoing light-like shell, a black hole is formed, which is generally described by a mixed state. So do these examples mean that a pure state is going to a thermal state, such as this? This, of course, cannot happen, because this is against unitarity. What we want to say is that from the perspective of some measurements or some observables, the long time behavior of the pure state becomes indistinguishable from that of the thermal state. So I'll go through several examples of such things. So this brings us to the concept of the reduced density matrix. So what set of observables show this property, the thermal property? So in a large class of systems, both theoretically and experimentally, it's observed that correlators of local observables at large times cannot distinguish between the pure state and a thermal state. Okay? So let's say you have some region A, and you take local operators, okay? And if you measure correlation of the local operators, then after a long enough time, you cannot figure out whether you started from a pure state, the whole system was a pure state, and you let it evolve for a long time. Then you can't figure out from within A that you started from a pure state, or you have always been in a thermal state or some other equilibrium state. So in more modern terms, this fact is expressed by introducing the concept of the reduced density matrix, okay, which is given by taking the initial state and tracing over the degrees of freedom of the rest of the region. So here one is assuming that the Hilbert space is factorizable, which is true for systems which do not have complications like gauge theories. So this is what the definition of the reduced density matrix is. So you define a reduced density matrix starting from a pure state like this. Okay, this is the definition of the left-hand side. And so that guy, as t goes to infinity, goes to this reduced density matrix of a microcanonical ensemble defined as that. Okay, where what is the what is the energy that you should assign to the microcanonical ensemble? That is the energy of this state. Okay, so typically in a quantum quench situation, after the quench stops, you have a certain initial wave function for the post-quench state, and the Hamiltonian now is something which is time independent. So the system has a conserved energy, and that's the energy that you should associate with this. This is called subsystem thermalization. So whether it happens or not, that of course is a matter of seeing it, doing the calculation and making some general enough arguments and so on. So in this talk, we would sort of focus on whether thermalization can happen in integrable models. So can we have thermalization in integrable models? So it has a lot of conserved charges. So for finite number of degrees of freedom, the half-dimensional phase space is described by conserved charges. Okay, so if you didn't have any constraint at all, then you had this entire shaded region as your space to move around. Then you have one more charge, you have one more codimension, you have one more charge, and so on and so forth. So eventually, whatever you're left with, is it enough to give you some kind of notion of effective ergodicity in this region? So it's not ergodic in the original sense of the word, but do you have some effective modified ergodicity? This question is not easy to answer and has not been answered in general for an arbitrary integrable systems in an integrable field theory. So partial answers are known for free field theories. We'll come back to these later in quite generality. But you can also find a general class of results for conformal field theories which are integrable. So that would be the first part of my talk. So you'll find in this case that, so not just in the free field theories case, but in the cases that I will describe, which will include free field theory and quantum quench, and also conformal field theories which describe the post-quench phase, which are integrable. So I will find that the system locally equilibrates to something called a generalized Gibbs ensemble, in which it's not the standard Gibbs ensemble that you have, but you incorporate all these other conserved charges, which are infinite number of them. So remember, I said that the system locally equilibrates to GG. Locality here means subsystem thermalization, the concept that I introduced in the previous slide. Note that global modes may not thermalize. Okay, so for example, if you take a transverse field Ising model, describe it in terms of these Jordan-Wigner fermions. So these are some situations which appear in spin models which can be realized experimentally. So if your focus is on this momentum modes, okay, and if you have some simple operators like this, they oscillate forever. Okay, they don't thermalize. Okay. On the other hand, if you go to local operators, then if the system is appropriate, then they do thermalize. So that's what I'm going to talk about mostly today. So I will talk about three different kind of results. One is about 2D, in which I do a critical quench. So after a quantum quench, the system, the Hamiltonian becomes a critical Hamiltonian. And I would give a general proof of the thermalization first, without the integrability aspect. It's just a conformal field theory, 2D, and I'll show how to prove thermalization here, and the rate at which various observables decay to their thermal averages. And then I'll give a proof of thermalization in integrable CFTs and the quantitative rate of thermalization. So it will have new results on critical exponents, the relaxation rates under such situations. So we will give a black hole interpretation of that. I will not take too much time on the black hole interpretation. I can describe that to anybody who is interested, because that's not the main subject of this conference. So then I would talk about thermalization. Excuse me, there's some typos here. Thermalization of non-relativistic Fermi gas. The results also apply to the hard core bosonic gas in the so-called Tonks limit. That's the extreme hardcore limit in so again in 1+1 dimensions. And the technique that we will use is something that I had used way back in the early 90s in the context of C=1 matrix model using phase space hydrodynamics, and we get some general results in that. Of course, phase space hydrodynamics has been mentioned in this morning, and I believe that it's been described in detail in Abanov's lectures. I was not present. But I'll explain what our results here are. And then some results about arbitrary dimensions, quantum quench in arbitrary dimensions, and thermalization for free scalar fields and fermions. So fermions we are able to do only in 1+1, but free scalar fields we have already computed exact treatment of quantum quench and operator correlators, and we find some interesting odd-even effect that things do equilibrate to GGE, local equilibration. However, the approach to the equilibrium in case of odd spatial dimensions is exponential, and in case of even spatial dimensions is power law. This is something that we still have not understood. Okay, so let me go to the first situation, critical quench. So here basically the idea is that we start from some Hamiltonian which has a time-dependent coupling constant, and so it can be slow like in Kibble-Zurek, or it can be a sudden limit of the quench. So the initial value of that coupling constant is G0, which makes the system massive, and the final value is G critical, which makes the system conformal field theory. A very simple example would be take a free scalar field theory in which this could be just the mass, and you begin with a certain mass and you end up with zero mass. So the mass is quenched from some non-zero value to zero. So the post-quench, the theory is described as conformal field theory because it's gapless. So most of the new sections in this results in this section will involve conformal field theories with an infinite number of conserved charges, although we will make statements about general conformal field theories. And so for us, the integral CFTs will be obtained in that the conserved charges will be obtained from local conserved currents of definite spin. And for definiteness, we'll consider these to be W infinity currents. However, our results will be valid for the general case as long as they are obtained from local conserved currents. Okay, so this is the figure written in equations now, that you end up with a conformal field theory. This is the action I'm writing here. And what this object is an operator with a non-dimensionless, dimension-full coupling constant, which accounts for a mass gap in the initial theory and gapless theory when you come to G critically. So that was a function G of t shown in the figure. So we'll consider for now a pre-quench wave function to be described by ground state. Okay, so our idea would be that we start from the ground state of the initial Hamiltonian, which is this. So this H is the Hamiltonian corresponding to the conformal field theory, and G0 O was the Hamiltonian initially before we started the quench protocol. Okay, so since time dependence is generally non-adiabatic, in case of a critical quench, of course, this is necessarily true because you are reaching a gapless theory, so it cannot remain adiabatic, so it has to be non-adiabatic. So the post-quench state at the end of the quench will not be the ground state. Okay, so in the case of an adiabatic evolution, you start with the ground state and your time-dependent state, it follows the ground state throughout, and you end up with the ground state. So here it will not be the ground state. So so this psi naught, the post-quench state, will not be the ground state of which I'm calling zero out of the new Hamiltonian, H out, which is just H in this case. So in particular, for a sudden quench, okay, the psi naught will be the same as the ground state. Okay, so you start with the ground state, and if it is a sudden quench, the system does not have any time to change. So this post-quench state is just the ground state of the initial Hamiltonian, which is not the same as the ground state of the final Hamiltonian. So that's what I've written here. And an explicit calculation of psi naught, okay, psi naught, is in general a different difficult task. Later we'll describe such a calculation in free field theories, but we will begin our analysis by using a certain ansatz for the post-quench state, which was introduced by Calabrese-Cardy back in 2005. And the ansatz was the following, that this is in the case of a critical quench, and it was this ansatz was made in 1+1 dimensions, but it can be generalized to higher dimensions as well. So what's the ansatz is that the post-quench state, so let us say that in the quench protocol, okay, there is only one scale that is involved, okay? So like there is a certain mass scale given by this G0, the initial value of the Hamiltonian. Then this was their ansatz, in which this kappa is something which is inverse of the initial mass gap. Okay, so a short motivation of why this is, and this BD is a boundary state, okay, which means that it's a state that you can introduce, okay, in a conformal field theory at a boundary, either at a space boundary or a time boundary. So what we have in mind here is that at time t equal to 0, the quench has happened at time t equal to 0. Okay, so at time t equal to 0, I have some state, okay, because of the quench procedure. I don't know what that state is, but I do know that if the scale, if the mass was, initial mass gap was infinitely high, then the resulting state cannot have a scale because I have sent that scale to infinity. So this has to be a conformal state. So at time t equal to 0, I have to invent a state which does not have any scale in it. Okay, so it's a state that does not break conformal invariance. So such states were written down in the context of 1+1 dimensional conformal field theory by Cardy, and in the context of string theory by Bacchus and various other people. These are called boundary states. It's a conformal boundary state. And now suppose that it was not really infinity, okay, but it's something very high. This mass gap was very high. Then basically the excitations in this state will be cut off by that mass scale, okay. So this kappa is something that is, 1 over kappa is that mass scale built out of G naught, which represents a UV cutoff for quanta in the system. Okay, so this was the thing. We'll first use this ansatz to prove thermalization and later critically examine the ansatz itself. We'll find that this ansatz needs modification in the case of integrable quantum field series. And in fact, even for free field series. All right. So these are the results that we get in case of the CC state. So there's Calabrese-Cardy state, CC. So consider the reduced density matrix of an interval A. So now we are talking about one spatial dimension. So my region A is an interval. So I'll take one connected interval for the moment for simplicity, but it can be generalized to multiple intervals as well. It's not too much of an extra work. Okay, so take that in a one-dimensional sample evolving like this, okay, in which now my time-dependent eigenstate is that this is, so this is the time dependence. There should be minus here and plus here. So this is the time-dependent post-quench state. It was at time t equal to 0. It was a CC state, and this is how it evolves. And this is my rho A pure. So we have been able to prove an exponential thermalization of the RDM. That is to say that this guy, this time-dependent reduced density matrix, goes over to a reduced density matrix of an equilibrium ensemble, which is a canonical ensemble. But of course, this temperature beta here is ensemble equivalent to the energy of the microcanonical ensemble, which I have already introduced in the context of subsystem thermalization. So this happens, and the rate at which this happens is that it's exponential. Okay, so and this relaxation rate is given as so. Okay, so first of all, there is some story about the equilibrium itself. Is that the effective temperature, inverse temperature, is given by 4 times kappa. Okay, so it's a very clean result. It's just 4 times kappa. And gamma min, okay, that refers to this following quantity is 2 pi over beta times delta min, where delta min is the scaling dimension of the most relevant operator of the conformal field theory. Okay, so here in proving this, we assume that the spectrum of scaling dimensions of the conformal field theory has a gap, and that gap is delta min. Okay, so this is some conjecture which was made by Cardy in 2014 and proved by us in 2015.
What does that equation mean?
Okay, very good. So basically what it means is that if I take the square normalized reduced density matrix on this side here, and take the square normalized equilibrium density matrix here, and take the trace of this times that, okay, what we prove is the following. What we prove is that the trace of rho A pure T, where this is not normalized in the usual way, this is square normalized. Okay, trace of rho hat square is equal to 1. And so this is also square normalized. It's just an additional normalizing factor that you have to do. And what we prove is that as t goes to infinity, okay, as t goes to infinity, you go to 1 plus some number alpha as e to the power minus 2 gamma times t. This is what we actually prove. And then here, these guys, after I have square normalized them, they are like unit vectors. Okay? So this is like the dot product of two unit vectors. So there is a vector v, which is time dependent, and then there is a fixed vector w, which is also time dependent, and these are unit vectors, and they go to 1 as time t goes to infinity, which means that this vector itself goes to this w0. And these quantities are all well defined. Of course, in doing this calculation, I do need UV regulators, but they do not come into this calculation. Okay, so so that was a very important question.
Excuse me, can I ask you a quick question? So what do you mean by the gap in the scaling dimension?
So, for example, if you take a scalar field theory in in non-compact space in 1 + 1 dimension, then there are these operators which are the exponential operators, like e to the power I k x, okay, where this k has a continuous spectrum, real spectrum. Okay, so such theories, I cannot handle by my method. Okay, but if I put the theory on a make it compact, so that this k then it starts from 2 pi over L, then that's the minimum. So the minimum scaling dimension in that case is k squared by 2, where k is 2 pi over L. So that's what. Okay, so so that's about the reduced density matrix. So that's the most general result through which you can make statements about local correlators, okay, of any number of operators, okay, which are all confined in the region A. Now, the system size is taken to be infinitely large compared to A, so therefore any number of local operators, correlation function of any number of local operators equilibrates through this equation. Okay, so that's a strong result. So, and a very important result which is used, in fact, to prove this is about one-point functions. So the one-point function, so this is a Heisenberg operator at CC. I mean, you can use either Schrodinger notation or Heisenberg notation. So as t goes to infinity, it goes like this, and where this gamma is related to the delta of this particular operator. Okay, so let me. Okay, so the reason why these exponentials come here is because of the conformal magic in 1 + 1 dimension, is that the expectation value of an operator, okay, in a Cardy-Calabrese state becomes as follows. So the Cardy-Calabrese state is like this. You begin, so this is the Euclidean time. You begin, at some Euclidean time tau equal to minus kappa, and then evolve by e to the power minus kappa h up to tau equal to 0. Okay, so this evolution operator here is an Euclidean evolution operator. Okay, remember that the CC state was given by e to the power minus kappa h acting on a boundary state. Okay, so the picture of the CC state is that whatever wave function you get by evolving from here by an amount Euclidean time kappa, when you reach here, that's your CC state. Okay, so if you want some expectation value of an operator sitting at this time slice itself, then you put that operator here, and then you are doing expectation value, so you have to double it up and do this strip functional integral. Okay, so, and when you want time-dependent stuff, what you do is to put some Euclidean time, so give it a little, kick off axis, and make this tau equal to IT. That analytic continuation is possible. So anyway, so this is how the picture of a one-point function, okay, including its time dependence, is that it's an operator, it's an insertion of a point, okay, in this strip. Okay, and that's what you have to do. You have to do the path integral with the operator insertion at one point. Now that is not so easy. However, in 1 + 1 dimension, this geometry is equivalent to the geometry of the upper half plane. Okay, and this point here, okay, it gets mapped to some point here. Now this becomes a problem of computing the one-point function, okay, in the upper half plane. Okay. That also by itself is not directly so easy. However, this problem can be, because there's a boundary state sitting here, this kind of problem can be mapped to the problem of a two-point function in which there's an image operator sitting here at P prime, in which this boundary is not there. So then it's a two-point function calculation in a plane. And that's just given by power law. Okay? But the thing is that the strip to the plane at the upper half plane, this is an exponential. Okay? So the power law here, okay, it just becomes an exponential when you take it back. Yes? Good. Right. So any conformal boundary condition will do. So this, this image, so there's a theorem proved by using conformal word identities, okay, which just uses the fact that this is a conformal boundary state, okay, which is given by the fact that. Yeah.
But it has discontinuity at zero, right? It's kappa and minus kappa. So it's. I mean, if I make a mapping, then from minus infinity to zero, it's kappa, and from zero to plus infinity, it's minus kappa.
Yeah, so it is like this. So this particular line goes like this. Take any point here, okay, go over there, vertically up. So that is like going from here to here. Okay. And various lines go like this, like that. That is how the map is. There is one important point which I should say, is that what you can say from here is that it's proportional to this exponential, but the proportionality constant, that depends on the boundary state. Okay? This guy here, okay, because it's not time dependent, so I have not bothered to write it. This is actually the one-point function, okay, of the this B here, this B here is of the operator O. Okay. So for some operators, it may so be that on that particular boundary state, okay, this boundary state does not excite an O like this. Okay. So then, the one-point function of the operator on that particular boundary state could be zero. So like, it could be in the Ising model situation, it could be all pluses. Okay, the boundary state could be like all pluses. Okay, and what you have as an O, okay, is some sigma 1 operator. Okay, so if you have all pluses and if you have a sigma 1 sitting in the middle, then you will get a 0. Okay, so that's so these are our results. In this, so this is about how one-point functions can be understood. That was result number 2, and the result number 1, which is about this, goes by this logic. And let me just say only diagrammatically here, is that the reduced density matrix, okay, has the following interpretation in terms of a path integral. It's just a cut plane. Okay, so the density. So this guy, okay, gives you. Okay, I don't know how I'm doing it at the time. 20 minutes. Yeah, maybe this is better to explain later on if I get some time. So essentially, a full path integral, okay, with so let me just say what this object is. A reduced density matrix, the matrix element of a reduced density matrix is given by the following path integral on this following geometry. So it's a strip, okay, with boundary conditions here and here, and only at this region at the interval A, there's a discontinuity, okay, and the lower end of the discontinuity, you put this wave function phi, okay, which is the wave function of the A part of the Hilbert space, and the upper end of the cut, you put the wave function psi of the Hilbert space. Here you are going on, here you are going on. So this is the tracing over the A of C. Okay, that's this. This fellow by itself is just e to the power minus IHT or e to the power minus 2 kappa H. Okay, with here. This is the Euclidean evolution operator with starting from psi and ending up at phi. This is that. And then you are tracing over the B region. I mean, tracing over the complement of A. So that's this. Okay, you are just, sort of gluing them. So that's the tracing. And then that should go over to something in which the strip has been replaced by a circle. Okay, it just becomes a cylinder. So the strip path integral should become a cylinder path integral with the cut. Okay, so that's the proof to be done. And this kind of a proof, this kind of a problem appears in the context of entanglement entropy, where such things happen, but with like geometries here, not unlike geometries here. So this required quite a bit of gymnastics to do a problem of gluing, okay, one geometry with another geometry. Okay, so there's quite a bit of technology here. This was done by using what is called a short interval expansion, first started by Matt Heydrich, and then developed by Calabrese-Cardy and Tony. Okay, so that completes the result and the sort of hint of the proof of how this goes for the general conformal case, where the Cardy-Calabrese ansatz is what we use. But then we found that the Calabrese-Cardy ansatz is too restrictive. In case of an integrable CFT, in fact, a more natural ansatz, which we have proved later on. So in this paper, so we say that, well, in case of an infinite number of conserved charges, this ansatz sounds more likely because you have, an infinite number of conserved charges. So why use only beta H, which is just one chemically? Yes. Hi.
But in your case, the QIs don't commute.
They do.
They always do? I thought in general what you get, so certainly what Cardy wrote, he wrote non-abelian charges.
Okay, so Cardy wrote other possible extensions of this in which there are irrelevant operators with perturbations.
No, that's not what I have in mind. So these are basically perturbations of the boundary state, now not just by the energy operator, but also by other irrelevant operators.
But so what my ansatz here is, what I call the generalized Calabrese-Cardy ansatz, is by this particular thing in which this QI fellows, they are conserved charges of a large algebra, okay, which, in which the conserved algebra, the conserved...
So is the
conserved currents.
So, but the QIs, they don't only commute with H, they also commute with one another. That's what you're saying.
Yes.
Ah, okay.
Yes. Of course, you could be even more general, as you say. You could, for example, here, you could say that I'm going to use non-conserved operator, just, integral of some irrelevant operator. That's what, that can also be done. That's even more general. But what we find is that in case of the quantum quench in free systems, okay, this is how it comes, even in higher dimensions. Okay, so our setup will be this, and as I said, after we wrote this paper about towards the end of that year, we were able to prove this in the case of quantum quench in free bosons and free fermions. So our setup will be this, that this will be integrable model with conserved charges coming from local currents, holomorphic and anti-holomorphic, as in a W infinity algebra. So there are examples of this, which are free fields, of course, and there are, so the representation of a W infinity algebra in terms of free fields have been worked out, way back by many people. And there are then coset models of this type, which have been made, more sort of well-known in recent times in the context of string theory, in the context of a sort of ADS-CFT-like duality between, the ON models, vector-like models, and some dual theory called Vasiliev theory. So Rajesh Gopakumar and Matthias Gabardiel introduced that duality, and the corresponding, these are interacting theories, the interacting conformal field theories of the coset type, which are of, which in the large n limit, large n, large k limit, they carry a W infinity algebra. Okay, and then there are parafermionic theories, which were discussed by Bacchus, and so on. There are other examples. Okay, so let's go. So with this, what happens? Now, unfortunately, this is not a geometric evolution, like, e to the power okay, here I should have called it kappa h, excuse me. Okay, this is not yet identified with something like a temperature. Okay, this is a pure state. Okay, I should really call it kappa h and kappa I here. This is a pure state acting on a boundary state here. I have missed that. So this is a pure state. Okay, and what will happen is that So let me go to that. The result quickly. Okay, this is a little bit of the technology. So what I wanted to say is that when such an operator acts on the boundary state, okay, this does not have the interpretation of a Euclidean evolution. Okay, this is not a strip because of these guys. Okay, they don't have any interpretation of that kind. Only Hamiltonian has an interpretation in terms of path integral like that. So we had to do a perturbation theory in this. We had to bring them down. Okay, so when you bring them down, okay, so you have to sort of do the calculation order by order and do a resummation. And there are some beautiful things that happen when these conserved charges are obtained from holomorphic and anti-holomorphic currents. And so the OPE technology, comes into play, etc. Okay, so let me just tell you the result. So this is about how resummation of those Feynman diagrams happens, and it gives you an exponential. And so what you get here is that the one-point function, okay, it evolves like this, e to the power minus exponential again, but the exponent here, okay, is modified, okay. So, and this modification is given by this mu are the chemical potentials which were already there, introduced in the Calabrese-Cardy state, and this Qi are the the algebraic properties of these operators. Namely, these are the W infinity charges of the operator O. Okay, and once you get this exponent, okay, you can find out the same story about the reduced density matrix thermalizing, just like, and you can relate the parameters of the quench protocol to the equilibrium parameters of the chemical potentials of the GGE. So this is a non-trivial formula because this does not merely follow from any conformal transformations. As I said, no magic of exponentials or something. You have to really do it the hard way. At least we don't know of any. Yes. Hi. Mu tilde is the dimensionalized, is the mu, guys. So it's mu I divided by beta to the power I minus 1. So basically, this is how it goes, that e to the power beta h minus mu I wi, and these wi's are, so w3, okay, has one higher dimension than h, w4 has two higher dimensions than h, and so on. So you have to divide your mu, okay, by some powers of beta to make it dimensionless. Okay. So, right. So there are two things that I would note about this formula. One is that when we first saw this, and then we saw this again in the context of our exact free field theory calculations, that this is a bit surprising that, you know, very long time behavior of a theory, okay, seems to care about, you know, coefficients of highly relevant operators, okay. These are all, yes.
Why do you find this surprising? Because in the sense your initial state deposits a finite energy density into the system, so a finite scale.
That's right. We found it surprising because the literature till then, there were many comments that, you know, for very long times, okay, it's enough to keep just the beta term, okay, or some effective notion of beta, some average effective notion of beta. But I completely agree that we introduce that's the explanation that in non-equilibrium physics, you don't do this usual Wilsonian kind of argument that at very long times only the relevant operators, because you have introduced by hand a very high scale. So that's indeed the explanation. Okay, so that, and then, so you know, the so-called UV-IR mixing is a sort of bread and butter situation in non-equilibrium physics. Okay, and this formula, oh yeah, so, and this formula turns out to have a holographic interpretation in terms of black holes, so just excuse me for the next slide, it's only one slide. So in string theory, in this ADS CFT context, what happens is that the zero temperature physics of a field theory, okay, is given by an anti-de Sitter space-time. Okay, the ground state of the anti-de Sitter space-time, and a finite temperature field theory is dual to a black hole sitting in that space-time. Okay, so this statement is true about both, is true about equilibrium situations. Now the approach to a black hole, okay, in the anti-de Sitter space is given by approach to a thermal state, okay, in the field theory. Okay. And therefore, okay, these relaxation rates that we found here, okay, should match, should match with what are called quasi-normal decays of scalar fields in that black hole, which so the dual black holes in this case are somewhat weird because the integrable theories, people normally think that the integrable theories cannot correspond to a black hole because it seems to go against no-hair theorems, because no-hair theorems permit only a small finite number of conserved charges. But these are something called higher spin black holes, okay, which do have an infinite number of conserved charges. And you can construct them, and you can also compute quasi-normal decay of scalar fields in that, and that quasi-normal decay rate exactly matches with the relaxation rate that we had in the field theory. Okay, this is, my string theory slide is over. Okay, so now in the last 7 minutes, let me say about the other two things. So, these are some results not in you know, not in conformal field theory or even relativistic field theories. These are in non-relativistic Fermi gas, which also applies to Planck's limit of Bose gas, which are also equivalent to matrix quantum mechanics. So if you take a matrix quantum mechanics, such as a unitary matrix quantum mechanics, you know, let's say we have some potential like this, which is, you know, this is a kinetic term like that, and it has a potential term, which is like a polynomial of u to the power n, u dagger to the power n. So in terms of eigenvalues, so, you know, so I cannot explain it now, but the eigenvalues of this Hamiltonian, they get a fermionic nature, okay? And they become like fermions moving on a circle, and they have some confining potential given by g and t across n theta I, and you do your quantum quench in this this time dependence here. Okay, So consider the simple model with only the n equal to 1 term. So that's g of t cos theta. And under a sudden quench from an initial value to a final value, the original ground state, which was like the Fermi C, corresponding to a slightly fatter cosine. Okay. Now, as you quench, okay, it has become a narrower cosine. Okay. And so the initial Hamiltonian can be, so what is the quantum mechanical way of doing it? Of course, you can do that. Okay, so the initial Hamiltonian can be described by one set of creation and annihilation operators, while the final Hamiltonian can be described in another set. So they are related by Bogoliubov transformations. So this is what Takeshi and I did in 2013. And using this above fact, you can do this thing numerically. That's the n equal to 120 result. What are we plotting here? So this is the first moment of the eigenvalue density, rho 1 of t. And so you start from some non-equilibrium state. I mean, you have done a quantum quench. And the first surprise that we had here was that it equilibrates at all, because at the time we didn't know all this stuff about thermalization in integrable models. So it equilibrated. The second surprise that was a nasty shock to us was that it didn't agree with the Gibbs value. Okay, so you could compute rho 1 of t, okay, in the Gibbs ensemble. Okay, that's this vertical bar. So it didn't go there. Then we learned about GGE. Okay, then we computed the GGE average of rho 1, and then the match was exact. Okay, so there are two values here. One is there are two plots here. One is the red one, another is the blue one. The red one is the n equal to 120. That's done by the exact quantum mechanical calculation. And n equal to infinity is what I'm going to describe. That's done by using phase space hydrodynamics method. So if you go to n equal to, if you take a large number of non-interacting fermions, you take n going to infinity and h bar going to 0 in some particular way, then its dynamics can be described semi-classically by droplets in the single particle phase space described by Euler's equation. So this has appeared in this morning's talk. I guess this has appeared in many, many talks in this conference. So this is, so what you actually get if you actually follow the some exact procedure, starting from the fermion path integral, going to the Wigner, phase space distribution and so on. What you get here is something called a Moyle bracket, which involves an h bar. Okay, so in the h bar going to 0 limit, the Moyle bracket becomes the Poisson bracket, and this is the equation given by the large n phase space density. So this is a phase space density. And the post-quench state is just given by some initial blob, some initial density. So, like, suppose that you had free particles in a box, then, suppose your initial density after some quantum quench was like this. Now, this is a phase space. So, fermions at different heights move at different speeds. So it gets distorted. So if you have a hump here, it gets distorted. And and also gets bounced. So after a while, you find all this, shreds coming in. And if you wait for, large enough time, all these shreds, okay, they all get averaged out, okay, in terms of something which is like a, thin gray area here. Okay, so, of course, actually, if you look at microscopically, it's only 1 or 0. Okay, phase space density of fermions can only be 1 or 0. Okay, but here, on an average, it seems that is interpolating from 1 to 0 in a continuous fashion. So this actually happens, and this is something that we had shown in this paper itself, but in a very recent paper with Takeshi and Manas. Okay, we have looked at this situation in a large number of quench protocols, and what we found was that this is very generic, okay, and this actually is given always by a GGE, and the approach to the GGE is power law, and depending on And then we got some general characterization of exponents. For example, if you had an x to the power 2m kind of potential and release it, and the particles are on a circle, then this the exponent eta here is given by 2m plus 1 divided by 2m, and then there are some other results. And it's not related to this work, but Takeshi, Manas, and I also did some using this phase-space hydrodynamic methods, using in fact these body fixed variables. We had a treatment of shock fronts. Okay, so I'll.
Sorry, can I ask a question about this? I mean, given the fact that your box is finite, of course it cannot relax. I mean, so the t equals infinity limit doesn't exist. So precisely how to understand this discussion?
So you're relating to the previous?
Well, no. I mean, so here you keep the box finite, right?
Yes.
And in a finite system, you can never relax, obviously. I mean, at asymptotic late times, you will have recurrences. Before there will be revivals, etc. So how to read these various pictures and formulas?
Right. So what happens is the following: that because of the multiple bounces, okay, that it just becomes this thin shreds. And we have actually, analyzed this quantitatively by looking at, the behavior of the fluid particle, okay, moving and bouncing and so on and so forth. And the time dependence is given by multiple images, mirror images and so on. And you can do all that. And there is a term which is like, so you have to do some Poisson resummation. And there is a term which corresponds to the, the zero Fourier mode of the Poisson mode. And then there are the non-zero guys. The zero Fourier mode of the Poisson fellow, that gives you this, gray thing. And then the other guys, generically, it's some, very complicated integral to finish and perform. But if you make some ansatses like these, then you can perform them, and you can find the long-time dominant behavior. So it's some power law. This is how. Hi.
I think I have a comment on this. I think what happens here is that if you take large n, then this recurrence time will be very far away, and this is a transient regime when you're still not at those times. So it's kind of intermediate ones. Of course, if you wait exponential long time with n, then you will get back original one, so it will return. But it's just some huge but intermediate times.
I see. Okay, I'd like to understand that as well. So, okay, I'm over time. So the third part, I'll just say, so forget about the technology, how this is done. So what we find, surprisingly, is that if we start from the CC state, and the same thing is true also for the GCC state, is that the and a correlation like this, phi RT, phi 0t, it goes over to this, as you expect. Okay, at long enough time from the quench, after the quench has happened, it goes to the thermal average. But in odd dimensions, it's always exponential. It's not given by the same exponent, okay, or there is no particular, organizing principle about the exponent that we found for various operators and so on. But the interesting thing is that if you do it for even dimension, okay, so these integrals we couldn't perform analytically, so we did this using Mathematica, and we found a perfect fit with 1 over t square here and 1 over t to the power, c is 2, so 1 over t square here, as you would expect, from a Green's function of that dimension, and 1 over t to the power 4. But we don't have an intuitive understanding of the ordinary difference. And thermal autocorrelator shows a similar behavior. This here we can do exactly, okay? And that also has an odd even difference. We have not understood this.
Sorry, is there any subtraction required? Or are these quantities actually finite for the quenches you consider?
If you want to look at the short time properties, then there is a subtraction required. Okay. Yeah. I see. You were saying that if I take a quantity which has an equilibrium value, indeed, that's right. So this is only I'm not sure whether I'm.
What I mean is, so in general, if I do a quench in higher dimensions, I have to worry about which quantity I look at. Because for most of them, they will be cutoff dependent, and one has to be very careful to.
Oh yes.
So is this a subtracted quantity? That's what I'm asking, or is
it is? It is. When I take when I take a composite operator, indeed I have to do a subtract thing. Yeah, I have to do a point split. I have to subtract out a singularity. Yes, absolutely. Okay, so these are the conclusions. We presented some result on how thermalization or more like GGization happens in integral systems. I have said it all. Thank you.
Okay, let's thank Gautam for the talk. Questions? Yeah.
Conformal field theory is only an approximate theory for condensed matter or for tabletop experiments in which it's only realized at low energy. So what is the application of your CFT results?
That's a very good question. Surprisingly, it turns out to be a rather difficult question. So, so you might ask, okay, let me say that I don't go all the way to a critical quench in which I take the final mass gap to 0. Okay, but I take the final mass gap to something small compared to the previous one. Okay, just to see the effect of a possible mass gap in the final system. So there are some. So there are scattered calculations of that kind of thing. Again, in the context of transverse field Ising model, there are a series of works by Calabrese. Where he and his collaborators, they find that depending on what quantity you're looking at, there is a or maybe I'm
okay. So given the fact that I'm an author of one of these papers, so maybe I can say so of course for transverse field Ising model you can work out everything off criticality quenching to on criticality, but I don't think that's the main limitation, because if you put the system at a finite energy density, if you have a small mass gap, so to speak, in your Hamiltonian, that doesn't really matter very much. So I think it's absolutely fine to work with a conformal field theory, in other words, because your scale that you put by hand is very high anyway.
Right.
Yeah. So I think that what Fabio was asking is the initial state, which has a very specific form for you.
Oh, how robust?
How can you make it?
I mean, if I take a ground state, then it's like automatically in the ground state of the initial Hamiltonian, no? I mean, if I take...
Yeah, okay, but so in order to get one of your initial states, as I understand it, you would need a fine-tuned Hamiltonian, a highly fine-tuned Hamiltonian. Because you only have these Qs, yeah, whereas the generic state you get is you have to act with infinite tower of irrelevant operators, not just the conserved charges on the boundary state.
Rather, I would say that if I have any gap, okay, then that gap itself translates to an infinite number of chemical potentials. So like beta depends on that, mu1 depends on that, mu2 depends on that. Everybody gets related to that one. So it's not fine-tuned in the sense that all the other chemical potentials are 0. In fact, they are never 0.
That's not what I mean. But so the operators you allow in your exponential.
Yes.
There's a very small subset of all irrelevant operators.
Oh, yes. Okay, compared to the other irrelevant, why am I not? Yeah, I see. Yeah, good question. I mean, we have looked at it. Cardy has looked at it. Presumably, I'm quite an outsider to this discipline. Maybe some people in the audience have looked at it. But we would like to say, some RG-like thing, as you were saying, that I can perhaps make some universal statements about just discharges being good enough, but we have not been able to.
More questions? Okay, if not, let's thank Gautam again.